Section 4.7, Indirect Argument, Contradiction, and Contraposition. So up till now we've done direct proofs. Now we're going to try other methods. They're going to seem a little bit strange at first, but these are still valid methods. So let's start with proof by contradiction. So we talked very briefly about this earlier, but we're going to say the thing we want to prove, in other words, the conclusion, we're going to say it's false. We're going to take the opposite of that, and we're going to put that as part of our given. And we are going to hope that that leads us to a contradiction, at which point we will then conclude the initial statement is indeed true. Here is one of the classic proofs of antiquity using this proof by contradiction to show that there is no greatest integer. So we are going to use proof by contradiction. So we're going to assume there is a greatest integer, which we are just going to call n. And so here's how I'm going to set it up, and you'll notice I'm stating very clearly that I'm using proof by contradiction. Let n be an integer such that n is greater than or equal to little n for every little n. Well, what if I add 1? Big N plus 1, that's an integer, and big N plus 1 is bigger than n. Well, that's a contradiction. I just said n is the largest, and now I've got one that's larger. So this is a fairly short one, but you can hopefully kind of see the logic that we're going to use. And you'll notice our very last statement, by contradiction, we're then concluding the initial thing we wanted to talk about. All right, we talked briefly about this as well. There is no integer that is both even and odd. I believe the proof for that is part of your homework, so we'll see what you can come up with for that one. Let's try this one. I've got the sum of a rational number and an irrational number, and we would like to show that that is irrational. And once again, I'm going to use proof by contradiction. So again, I'm going to assume the opposite. So I've got real numbers, R and S. R is rational, S is rational, and again, our initial conclusion is that R plus S is irrational. Again, that sum is irrational, but because it's a proof by contradiction, part of my given is I'm also going to assume that that sum R plus S is rational. So if we remember our definition for rational, we could write it as a fraction of two integers, where of course the denominator is not equal to 0. And then I'm going to start substituting them. Here S is irrational, so that's why we don't have a substitution for that. And then let's move those fractions to the same side so I can combine them and write them as one big fraction. Well, we did a problem like this similar earlier on. That is going to be rational because we've got adding, subtracting, and multiplying. That's all still going to be rational. The denominator is not 0. So I've just said that S is irrational. But remember, we said S is irrational. And there is my contradiction. I've said an irrational number is equal to a rational number, and I can then make my conclusion that my original statement, the sum of any rational and any irrational number, is irrational. All right, that was proof by contradiction. Let's look at contraposition. We did contraposition earlier. Remember our regular if P then Q. The contrapositive is if not Q, then not P. And we said that those two are logically equivalent to each other. So again, I'm going to take my initial statement and I'm going to rewrite it as the contrapositive. I usually recommend writing it out because I like to clearly state what my given is and then also clearly see where I like to end up. At that point, I do a direct proof like I would normally do. Again, I am going to ask that rewriting with the contrapositive, I am going to ask that you do please include that. I like to see that. So let's see an example where that's helpful. Here, for every integer n, if n squared is even, then n is even. It is really hard to go from something bigger to something smaller, especially if it would involve taking a square root. Square roots are incredibly messy, as we know. So this is a great example of a problem where using that contrapositive is really going to help us out. So again, I'm going to start by stating that contrapositive. If n is not even, then n squared is not even. Well, if it's not even, that means it's odd. So phrased more neatly, if n is odd, then n squared is odd. And we have actually already proven that. That was a couple of sections ago. So that would be the rest of the proof is what we have seen in previous sections. All right, now these can be a little bit confusing. They sound very similar to each other. So again, contraposition, I'm going to change the initial statement and then do a direct proof. For contradiction, though, I am going to assume not Q as part of my original problem, and then hopefully discover that not P is going to end up happening, which is where my contradiction is. So again, they do sound very similar, but there are some differences between them, so please be careful as you work through this homework. We will see both types, and yes, they are different. And this is everything in section 4.7.